Hello everyone, my name is Kristen Atkinson and I'm a product marketing engineer here at Texas Instruments. And today I'll be talking to you all about driving the future of CAN, EMC-compliant automotive 3.3 volt CAN transceivers. Before we get started, I would like to encourage you to ask questions throughout the presentation using the Q&A box, where we will have Danny Basic standing by to answer questions in real time. And we will also be conducting a Q&A at the end of the presentation. All right, so today we will be talking about why to use 3.3 volt CAN and how it simplifies your design. I will then introduce the industry's first EMC-compliant 3.3 volt CAN transceivers and go into some details about interoperability between 5 volt CAN and 3.3 volt CAN, as well as EMC compliance. Lastly, we will conclude with a getting started guide. As vehicles include more advanced features for comfort and safety, it is becoming crucial to maximize power efficiency. Power efficiency not only lowers operational costs, but also enables longer driving ranges for electric vehicles. To simplify power design and increase power efficiency, many electrical components, such as microcontrollers, are lowering the typical supply voltage from 5 volts to 3.3 volts. Why is it beneficial to use 3.3 volt CAN? As I mentioned, the supply voltage for many electrical components are lowering to 3.3 volts. In many automotive systems, a 5 volt power rail is only needed for the 5 volt CAN transceiver, while all other components can use a 3.3 volt or lower supply rail derived from the battery. If the 5 volt power rail can be eliminated, and the CAN transceiver as well as all other components can use 3.3 volts, this would reduce board space and BOM cost. 3.3 volt CAN transceivers and 5 volt CAN transceivers are interoperable and can be used on the same bus. This is useful for changing select nodes that would benefit from eliminating the 5 volt power rail and reusing other nodes where 5 volt rail is needed for other components as well. Previously, it was a challenge for 3.3 volt CAN transceivers to pass EMC requirements. But due to proprietary design techniques, TCAN 340X-Q1 family is the first 3.3 volt CAN transceivers to pass IEC 62228-3 emissions testing in homogeneous and heterogeneous networks. Let's look at a simplified example of an automotive CAN node. In this example, separate 5 volt and 3.3 volt power supplies are needed to power the CAN transceiver and CAN controller respectively, since the CAN controller is likely housed in an MCU that requires 3.3 volt power supply. If the 5 volt CAN transceiver was replaced with a 3.3 volt CAN transceiver, then the 5 volt LDO could be removed from the BOM, which would result in reduced cost and reduced board space. Let's talk about interoperability between 3.3 volt CAN transceivers and 5 volt CAN transceivers. The CAN standard ISO 11898-2 2024 requires a common mode voltage range of -12 volts to +12 volts. As you can see in the image on this slide, 3.3 volt CAN transceiver recessive biasing of CAN high and CAN low terminals is 1.89 volts. You can compare this to a standard 5 volt CAN transceiver where the recessive biasing of CAN high and CAN low terminals is 2.44 volts. This minor shift in common mode voltage is compliant to the ISO standard and is inconsequential compared to the extended plus or minus 30 volt common mode voltage range of TCAN 340X-Q1 family. ISO 11898-2-2024 also requires VOD of 1.5 volts for the transmitter and VID of 0.9 volts for the receiver. 3.3 volt devices are above these requirements and allow seamless communication with any other ISO 11898-2 compliant transceivers, such as any 5-volt CAN transceivers. So therefore, TCAN 340X-Q1 family is fully interoperable with other transceivers on the same bus powered by a 5-volt supply. This is TI's first family of automotive qualified 3.3 volt CAN transceivers to meet EMC standards. These devices, TCAN 3403-Q1 and TCAN 3404-Q1, share many features, such as plus or minus 30 volt common mode range, data rates up to 8 megabits per second, and bus fault protections up to plus or minus 58 volts. These devices also have a few unique features. TCAN 3403-Q1 has I/O level shipping capabilities from 1.7 volts to 3.6 volts, and it also has standby mode. TCAN 3404-Q1 has shutdown and standby modes for low power applications. These devices can be used in many applications, but just to name a few, they can go into body electronics, advanced driver assistance systems, and zone architecture. These devices are available in 3 different packages: industry standard SOYC-8, VSON-8, but also in a uniquely small 810 SOT footprint that saves up to 70% PCB board space over the SOIC-8 package. Meeting component level EMC testing is a strict requirement for CAN transceivers to be qualified at major car makers. To meet EMC requirements, significant design effort has been made in TCAN 340X-Q1 family to keep switching symmetry between CAN H and CAN L during rising and falling bus transitions. Additionally, proprietary design techniques are implemented in TCAN 340X-Q1 family that dynamically adjusts the bus common mode while driving and receiving CAN data to meet emissions, specifically in heterogeneous networks. Emissions in networks where all nodes on CAN bus are 3.3 volts is easier to meet compared to networks where there is a mix of 3.3 volt and 5 volt CAN nodes on the same bus because of the movement of common mode during the recessive condition. TCAN 340X-Q1 family of devices meet the strict EMC requirements per IEC 62228-3-2019 under both homogeneous and heterogeneous network conditions. This Getting Started guide includes additional information about TI's new 3.3 volt automotive CAN transceivers. There are multiple articles that include further information about 3.3 volt CAN, as well as an EVM to jumpstart your development. You can order samples of these devices by viewing the product folders and navigating to the TI store. I want to thank everyone for joining today's presentation. If you have any additional questions, please put them in the Q&A box, and we'll be sure to reach out to you directly. Thank you again. Okay, so we're going to start with some questions. So these are questions that you guys are submitting in the Q&A box. The recessive output voltage range of 3.3 volt transceivers is 1.5 volts to 2.25 volts, which is lower than 5 volt powered CAN transceivers, which is 2 volts to 3 volts. Does this cause any issues on a mixed node network? So our new generation of 3.3 volt CAN transceivers, which is the 3403 and 3404 Q1, are designed for interoperable communication in mixed 3.3 volt and 5 volt networks. This recessive voltage difference with 5 volt CAN is not a concern since CAN is a differential interface and the differential voltage requirements are being met by both the transmitters and receivers for 3.3 volts and 5 volt CAN. If we have a common ground system with two CAN nodes talking to each other, one at 3.3 volts and one at 5 volts, it seems that there would be a common mode current flowing from the 5 volt node to the 3.3 volt node in both recessive states and dominant states, or in states where 5 volts is trying to dominate. When a transceiver is recessive or not transmitting, it's largely high impedance to the bus, so it shouldn't be sourcing or sinking very much current. This has been considered when we designed the 3.3 volt CAN transceivers, so you shouldn't see this happening with these new 3.3 volt devices. Another question, does my 5 volt CAN node need to have 3.3 volt VIO pin to be on the same bus with the 3.3 volt CAN transceiver? So the VIO pin of the 5 volt CAN transceiver only impacts TXD and RXD voltage levels between the device and the MCU. So the CAN bus is not impacted by the voltage level used on VIO. So for the 5 volt CAN node, it does not matter whether that device needs VIO capability, as it's just determined by the allowable voltage levels of that node's MCU. Okay. Have you evaluated EMC performance for TCAN 340X-Q1 in heterogeneous and homogeneous networks? Yes, our new 3.3 volt family meets IEC 62228-3 standard for EMC performance in both heterogeneous and homogeneous networks. Is it possible to get EMC reports of TCAN 3404? Yes, you can reach out to the Customer Support Center and we can provide those EMC reports. What is the price difference between 3.3 volt and 5 volt CAN transceivers? So you can see this price difference on our TI store. So since these devices have been released already, they have 1 KU pricing already. So you can just compare like the pricing of the 3403 or 3404 to like a TCAN 1044 pricing to get a comparison there. Are the parts already in mass production? Yes, they are already in mass production. We have 3 different packages, and these are all released already. So you can find those on ti.com. Will there be an isolated version? There will probably be an isolated version in the future, but we have not started development on it yet, as these are our first devices that we were releasing to the market, and we were focused on having these be accepted first. But that is something that we will be looking into in the future. Any 3.3 volt 14-pin parts in the pipeline with more mode pins and inhibit functionality. Yes, so we have already started working on the 14-pin device similar to our 1043A and 1043N. So these will be coming in the future. Okay, so this question was already answered in the chat, but I'll just read it out so everyone can hear. With the TCAN 3403-Q1, what is the pin capacitance of TXT or RXT with respect to ground? The pin capacitance of the digital pins for these transceivers are similar to the standard 5-volt transceivers that have already been on the market. The datasheet of the TCAN 3404 lists the TXT pin capacitance at 4 picofarads for typical. But these data sheets are public on CI.com, so anyone can go look at those specific specifications. Is there any low-speed chips with these features, TCAN 3404-Q1 expected in the future? Because of the ISO standard for the data rate for CAN-FD, the maximum data rate is 5 megabits per second. We won't be designing any lower speed chips because we want to be, compliant to the latest ISO standard, and we want to make sure that our devices, have the maximum capability that they can have. So we will not be developing any lower speed devices. We will just be adding different features, like I said before, the 14-pin version with wake and inhibit and those kinds of things, but not any lower speed devices. Okay, any guidance on implementations for 48-volt systems? So depending on the 48-volt system that you are designing, if we're talking specifically for electric vehicles, it should be a similar implementation as, the CAN architecture you've been designing before. So kind of what the feedback that we've been getting from the market is that 58-volt bus fault protection should be good enough for 48-volt systems if it's like an electric vehicle where load dump is not an issue. So if you're designing a system where you're not expecting any load dump conditions, then 58-volt bus fault protection should cover your needs. You'll just need to calculate your transient voltages and be sure that that does not exceed 58 volts. But if your transients don't exceed 58, then TCAN 3403 and 3404 should work in your system. Okay, is this IC qualified for automotive standard? Example ISO XXX. So currently ISO 11898-2, they just did an update in 2024 before this device came out. So currently that ISO standard does not include 3.3 volts, but there is a special interest group working in Canon Automation to have this standardized and basically standardize the interoperability between 5 volts and 3.3 volts. So it is being worked on right now, and it is going smoothly. So yes, there is a special interest group working on this standard, but it's not currently included in the ISO 11898-2 standard. Is it AEC 100 qualified? Yes, this is AEC Q100 qualified for automotive applications. Both the TCAN 3403-Q1 and 3404-Q1. So on our part numbers, the -Q1 signifies that it's AEC Q100 qualified and can be used for automotive applications. In this family, we have also released industrial versions. So we have TCAN 3413 and 3414. These do not have the -Q1, and these are for industrial applications, but they are part of the same family of devices. So if you have an industrial application, then I recommend you go check out the TCAN 3413 and 3414. So if you're using an older generation of 3.3 volt parts like the SN65 HVD 230, will there be any differences, or what is specifically new with our new 3.3 volt transceivers? So the older transceivers like the SN65 HVD family was not designed with EMC in mind, so the EMC performance is not comparable with this new TCAN 340X family. If this isn't a requirement, like this is an industrial system, or EMC is not a concern for your application, then you can still continue to use those older devices. But we are using, the latest and greatest process technology for our new family, and it also has other advantages like increased ESD protection and things like that. So there are other advantages, higher data rates, that kind of thing. There are advantages to using the new TCAN 34XX family. Okay, are there any changes or differences in common mode chokes in 3.3 volt designs? The same common mode chokes can be used for 3.3 volt CAN systems as well as 5 volt nodes. So you can just keep using your same common mode chokes and implement them the same way. Okay, are there any limitations to the maximum cable length? So the limitations for 3.3 volt CAN transceivers are similar to 5 volt CAN transceivers because the output voltage on the bus is the same for both solutions. So the limitation is still unchanged. So the same limitations you'd have with a homogeneous 5 volt network will be the same for a mixed node network of 3.3 volt and 5 volt systems. Okay, so can we consider to use a TCAN 3404 to replace TCAN 1044? So yes, the only system level difference will be switching the 5 volt supply pin or supply input with a 3.3 volt supply input. All other pins remain the same with other 5 volt CAN transceivers such as TCAN 1044. So you can use 3.3 volt transceivers. They're most beneficial in systems where the 5 volt rail is only needed for the CAN transceiver, as explained in the presentation today. So how to convince customers that 3.3 volt CAN does not affect the overall vehicle system apart from change in voltage rail. Currently, the EMC test reports, conformance test reports, and demos that we have, as well as EVM boards, those are good resources to share with the customers to help gain their confidence in this new technology. But you can, put in a 3.3 volt device mixed into your current system, and you should not see any change, or I guess you shouldn't see any reliability issues with your messages being communicated. So yes, you can use all of these tools to gain confidence. You can also share some of those resources that were in the getting started slide of this presentation. There's a white paper that goes into specific details about the interoperability between 3.3 volt and 5 volt, as well as the EMC performance. So these are all great resources to share with your customers, to help them gain confidence in this technology. Does it impact the number of nodes in the network? So the common mode load for TCAN 34XX is similar to that of 5 volt CAN transceivers, so similar to the answer with the cable length limitations. You'll have the same limitations with the 3.3 volt CAN transceivers that you would have with the regular 5 volt CAN transceivers. Okay, so I believe we're out of time for this webinar. So I want to thank everyone for joining today. And if you have additional questions, please put them in the Q&A box, and we will be sure to reach out to you directly to get your questions answered. So thank you again, and have a great day.